diesel cycle. Okay, so this will be the second example for diesel cycle. So now calculate the cycle efficiency and mean effective pressure of an A standard diesel cycle with a compression ratio of 15:1. Basically, this will be the volume ratio. Otherwise, it's stated as, let's say, for example, sometimes it refers to pressure ratio, it would be stated. So the compression ratio here actually refers to the maximum volume divided by minimum volume. So to have a volume ratio of 15:1. So they have given us the maximum and minimum cycle temperature of 1650 and 15 degrees C. And then they have given us the maximum cycle pressure of 45 bar. Remember the temperature, we have to add it with 273 to change it to absolute temperature. So this will be your PV and TS diagram. Basically, when you look into this PV diagram here, these red lines here, they are the reversible isentropic processes. Okay, so these two paths here, they follow the law of PV to the power of gamma equals to C for isentropic. And then this would be your constant pressure on the TS diagram. And then this would be your constant volume, which is on your TS diagram to be a curve. Okay, so basically the volume line should be steeper than the pressure line. So you have two reversible isentropic processes, one constant pressure process and another one constant volume process. So when you refer to state point 2 to 3, which is constant pressure, and also it is a heating process or heat supply, which you can see based on this arrow here is an increasing entropy direction. And then 4 to 1 here, which is the constant volume process. Okay, so that is the decreasing entropy. So this is the increasing entropy and this is the decreasing entropy. So you have heat supply here and heat rejected to the disk. Okay, so and the cycle go in clockwise direction. So I can note here. So the red lines here refers to the reversible isentropic or adiabatic processes. Reversible, adiabatic or isentropic processes, which follows the law of PV to the power of gamma equals to C, which you can mark it on these two curves here on the PV diagram, not on the TS diagram. On the TS diagram, you cannot put both of these follow this law. This is only referring to PV. Okay, so and then the blue line here refers to constant pressure, and this is a heating process, heat supply. And then the green line here refers to isochoric or constant volume process, okay, which refers to heat rejected, okay, a heat rejected process here or cooling process. And then for your knowledge, okay, or reminder, okay, increase in entropy means heat supply, decrease in the entropy when you refer to the TS diagram. Decreasing entropy is actually cooling or heat rejected. So heat supply, that means heat energy flow into the system. Heat rejected means the heat that is flowing out from the system. So expansion process refers to increase in volume, that is from 0.3 to 0.4 here, as you can see, okay, that is the increasing volume. So an expansion process, usually work is done by the system. So basically we will call this as the work output. And then the compression, that is here from 1 to 2. So for increasing or decreasing volume, usually we refer to PV diagram, increasing or decreasing volume. Increasing entropy or decreasing entropy, usually we refer to the TS diagram. So compression, which refers to decrease in volume, that means the work input, okay? So work is done on the system. So isentropic or adiabatic, that's these two lines here, as you can see, is constant entropy, okay? Constant entropy. So that is the isentropic or adiabatic process, means there's no heat flow. Constant volume, that is here, you can see the change in volume will be 0. That refers to no work done. So you cannot take work done based on 4 to 1. You cannot take heat flow from 1 to 2 and 3 to 4. Okay, so as a reminder from the heat engine cycle that we have drawn earlier, okay, basically from the energy balance from the heat engine, we got net work out equals to heat supply minus heat rejected. From the word net work out, it can also be referring to work out minus work in. So in other words, you can say work out minus work in is actually equals to heat supply minus heat rejected. So basically, you can also say that the net area of your PV diagram should be equal to the net area of your TS diagram according to the second law of thermodynamics. Now let us go back to the question. Now calculate the cycle efficiency and mean effective pressure of an A standard diesel cycle with a compression ratio, that means the volume ratio of 15 to 1, which usually refers to Vmax over Vmin, the volume, maximum volume over minimum volume. Then the maximum and minimum cycle temperatures, they are 1650 and 15 degrees C. So you can add this with 273, this with 273, so become 288 Kelvin. So usually we convert it into absolute temperature Kelvin. And then the maximum cycle that pressure is 45 bar. So this is the table which I have prepared and I have put in red for those given in the question. The data that is given in the question, I mark it in red. So those in black, we have to find out one by one. And this will be the cycles. So for this, let's say it refers to this state point 1 to 2 here, which is the isentropic compression. Isentropic compression process. Compression, as you can see, the volume decreases from V1 or V4 to V2. So, and it is an isentropic process, so that is why we call it as isentropic compression. So based on the isentropic or adiabatic relationship between pressure and volume, make sure this is power of gamma. If temperature to volume, this should be gamma minus 1. If temperature to pressure, then this should be gamma minus 1 over gamma. So for A, usually we consider gamma as standard 1.4. It's stated here A standard diesel cycle. So the A is gamma. Okay, gamma for A is 1.4. And then based on the relationship here, if let's say, for example, you put P1 over P2, you should have V2 over V1. If you put P2 over P1 here, you should have V1 over V2. So from this, you can find out the pressure of 1.02 bar. So then after that, you can come back to this step here to find out the volume here. Because we have known the temperature, which is given 15 degrees C plus 273, so you got 288. And then the pressure is 1.02. Okay, so using the ideal gas law, use PV equals to RT, PV equals to MRT. If you use PV equals to MRT, unless the mass is given. So the pressure, the specific gas constant for A is standard 0.2871. And then the temperature in Kelvin, this is the temperature, 288. So you will be able to find out this volume here. So based on the compression ratio, which is the volume ratio, that is this, or you can take Vmax to Vmin here, that is V1 to V2, okay, is given as 15 to 1. So that is why you have this. I come back to this again. It's 1 over 15 because it's V2 over V1. Then based on that compression ratio or volume ratio, actually we can find out V2 because we have already known the V1. Okay, so this is 15, not 6. So you will be able to find out the V2. And then after getting V2, now we can get, or we can find the temperature of T2 by referring to the ideal gas law one more time. Okay, for state point 2, you can find out the temperature of 846.4 Kelvin. Now, my advice is, okay, try to fill up all these unknown data here that are marked in black. Yeah, okay, all these unknown data here, find each of them one by one. So we have got state point 1 completed, state point 2 completed. State point 3, the question have given us the pressure and the temperature. So we will be able to find out the volume by using ideal gas law. Okay, so this will be the ideal gas law finding out the V3. So once we have found out V3, yeah, okay, so write it down on the table. So you got state point 3 completed. Now what is left over is only state point 4. State point 4, when you refer back to your PV diagram, you can see that V4 is equals to V1 here. So that is 0.81. So that is why I write a 0.81 as well. So from this, you can see this is unknown yet. This is still unknown. So you have two unknowns. So basically, when you refer to 0.3 to 4, which is isentropic, again, you can use the isentropic or the adiabatic relationship between pressure and volume if you want to find pressure. Between temperature and volume if you want to find the temperature. So this is what we have. So remember, gamma is 1.4. Okay, and the pressure ratio, the volume ratio should be inverse. So then you can find out the P4, which is 3.215 bar. Then after that, you can find out the last one, that is the temperature T4, by referring to the ideal gas law again. So you will be able to find T4 with the pressure P4 found with the R, which is standard 0.2871 kilojoules per kg, K, and then the specific volume, which we have the data from the given question, from the question given, so 0.81. So you got your T4. So once everything is found, everything is complete here, then the next thing you must think of is your heat supply and heat rejected. So remember your heat supply, that is 2 to 3 increasing entropy, heat rejected decreasing entropy. So 2 to 3 is constant pressure. So for heat supply at constant pressure process should be Cp multiplied by the temperature difference. And why is Cp times temperature difference? Remember, during constant pressure process and the non-flow or the steady flow energy equation, you will be able to find out the heat flow by converting the H to Cpt. So that is why you have Cp T3 minus T2. Okay, so you have found heat supply here with the temperature in Kelvin. Cp given, or Cp as for A is actually 1.005 or 1.006 is standard for A. Okay, then the next thing is your heat rejected from 4 to 1. Okay, so 4 to 1 is a constant volume process. So that is why I use Cv, because heat is equal to the change of internal energy here. And internal energy is equal to CVT. So that is why I have CVT4 minus T1, that is the temperature difference between 0.4 and 0.1. Okay, for A is standard, Cv is equal to 0.718 kilojoules per kg. So you will be able to find out your heat rejected. So once you have found your heat supply, heat rejected, the most important thing is your net work out. So your net work out is basically equals to heat supply minus heat rejected. So put in your heat supply and heat rejected. So you'll be able to find out your net work out at 638.55 kilojoules per kg. Then the thermal efficiency, since thermal efficiency is defined as net work out over heat supply. So this is your net work out and the heat supply is 1083. So you have your thermal efficiency of 59%. Thermal efficiency basically is defined as the desired output for all heat engine is the net work out. And the required input is your gross heat or the heat supply. Then the next thing is your mean effective pressure is defined as net work out over length of PV diagram. So we have found the net work out. So the length of PV diagram, let's take a look at the PV diagram now here. So the length basically refers to the outermost 2 points. So you can refer to point 1 or 4 here, okay, for this line, for this point. Then you can have the innermost one is your point 2. So that will give you the length. So you can take V1 minus V2 or V4 minus V2 as well. So that would be your length of PV diagram. So put it in as volume. So you will be able to find out your mean effective pressure, 844.64 kilonewton per meter square, or you can change it to 8.44 or 8.45 bar. Okay, that's all for this example. Thank you and stay safe.